Hi everyone, this is Chunxu Tang from Twitter. Today, I would like to talk about the experience of development of the Presto Iceberg connector at Twitter. So there are mainly two sections that in this presentation. For the first section, I would like to introduce a little bit more about the Presto ecosystem at Twitter. And then for the second part, I would like to concentrate on the Presto Iceberg connector. So for the first part, I would like to talk about the Presto ecosystem at Twitter. At Twitter, actually, we are maintaining a really large Hadoop clusters. So it means that we have a really large amount of data. So in that case, to maintain the Presto ecosystem, there's really a long path for us pursuing for scalability and availability. So here is the basic statistics of Presto at Twitter. We have more than 9 clusters. Some of them are on-premise, and some of them are on the cloud. And we are having more than 3,000 Presto workers. And for the whole Presto cluster at Twitter, we have executed more than 16 mailing queries. So this is really a large cluster. So in that case, there will be some issues related to scalability and availability that we need to resolve. That's why we proposed a Presto federation system, where we introduce a Presto router service among the customers and the Presto clusters. So with the advent of the router service, when the customer send a request to a Presto ecosystem, the client will just send a request to the router, and the router will apply kind of scheduling mechanisms such as round robin or fixed routing to route the request or redirect the request to a specific Presto cluster. So in that case, the customer doesn't need to directly send a Presto cluster by memorizing the specific endpoint of that. This will give us some benefits. For example, for the scalability, this makes the whole system very easily scaled out. For example, when we want to add a new Presto cluster, we can just add the cluster and register the information in the Presto router side. So in that case, when a client sends a request to the Presto router, the router can help to balance the workload across different clusters and sending some requests to the new Presto cluster. So that's also why for the scalability, the waiting queue will be split to subclusters to help us to balance the load onto different clusters. And on the other side, we also have aggregated UI and APIs set up for the Presto router service. So in that case, we don't have to check the UI of each Presto cluster one by one, but we can directly monitor the whole status of the Presto ecosystem by checking the aggregated UI provided by the Presto router service. So that's for the scalability. And for the availability, we are using a rolling deployment strategy. So in that case, even though sometimes one Presto cluster may be offline, but there's still some clusters are online. And then when the customer sends a request to the Presto router, the router will just route the request to the existing clusters. So those are some benefits of the Presto federation system. But we are still seeing some issues when maintaining the previous federation system, such as sometimes we find that there's still unbalanced workload onto different Presto clusters. So that's why we also propose an intelligent cluster management system where we introduce 2 more modules. One is a query predictor, and the other is a query scheduler. The purpose of the query predictor is to predict the expected resource usage of each SQL query. With this kind of information, the query scheduler will help to intelligently schedule different requests to different Presto clusters. One interesting point here for the query predictor is that we introduce machine learning algorithms to try to help us to estimate the CPU and memory resources expected for each SQL query. So here is a high-level design of the query predictor service. First, we have some Presto logs. These are some logs generated from historical queries. So with these request logs, we apply some machine learning mechanisms such as random forest or XGBoost to train two models from the previous Presto logs. One is a CPU model, which is used to predict the CPU time of each SQL query. And we also have a memory model, which is used to predict the peak memory bytes of each SQL query. And then with these two models, we assemble them into a predictor service. So in this case, for example, a customer send a request to the router, and the router may forward the query to the predictor service to get a sense about the resource usages needed for SQL query. At Twitter, we have also open sourced the whole code base of the query predictor. We have put it in the Twitter Fox Presto repository. Also, with this, we created a web application for the query predictor, where there's a form that a user can just fill in some SQL statements in the form and click the predict button to get an expected CPU time and peak memory bytes of each SQL query filled in the form. So that's mainly about the work that we have done at Twitter. So that's mainly for the first section. And then for the second section, I would like to introduce more about the Presto Iceberg connector, which is used to empower SQL queries on the open table format. I know that some of you folks may not have much background of Apache Iceberg. So here I would like to give you some quick introduction about this open table format, especially suited for huge analytic datasets. There are some very useful features for Apache Iceberg. I list some of them here. There are some schema evolution, hidden partitioning, partition layout evolution, time travel, and version rollback. So take the first schema evolution as an example. So in the modern data platform, it is quite common that sometimes we may need to change the schema of a data set. For example, we may add a new column, we may drop a column, we may rename a column, etc. So this kind of mechanism, the schema evolution, is naturally supported by Apache Iceberg. So in that case, we don't have to worry about the change of the schema will break some queries. And this will be handled by Iceberg itself. For hidden partitioning, it means that we don't need to explicitly assign a partition to a table, and this can be handled by Iceberg underneath. And also it points to another feature, partition layout evolution, which means that not only the schema can evolve, but the partition can also evolve. For example, for a table, previously we may partition it, for example, by dates, but then we may change the partition to partition it by month. So this kind of thing can automatically be taken care by the Apache Iceberg table. And also there are some other useful features like time travel that a user can travel back to a specific timestamp to run some queries against that table. And then there's also a version rollback that a user can roll back to a specific version. So here are some very useful features of Apache Iceberg. And for the next, let's maybe have a little bit deeper dive into the structure, into the format of an Iceberg table and see what is the inner mechanism of it. There are some keywords or some important specs of Iceberg table. I put them here, like snapshots, manifest list, manifest file, partition spike, partition tuple, and snapshot log. Snapshot is kind of a state of a table at a specific timestamp. For example, we may have a snapshot 0 or snapshot 1 shown on the diagram on the right. And then we may have a manifest list. So each snapshot will have a manifest list, which points to a list of manifest files. Each manifest file will store some metadata information of data files. So in that case, a manifest may point to multiple data files, and each data file store the data set. And then we may have the partition spike. Partition spike is it's just about how to partition the data in a table. And then partition tuple is just a tuple or a struct of partition data stored in each data file. And then we have a snapshot log. Snapshot log is stored in a table metadata. It's just about the log of snapshots. So here is a high-level description of the format of the structure of an aspect table. So maybe it's better to go with an example to see how it really works. So here I want to introduce an example. This is an example from the TPCH dataset. We especially created an aspect table from the region dataset. In the region dataset, there are 3 columns: region key, name, and comment. So this is the aspect table created from the TPCH region table. There are 3 files: manifest list, manifest, and table metadata. On the left, here is the manifest list. It is actually stored in an Avro format file, but to make it more human readable, we convert it into a JSON format. So you see here it has a manifest path. It has like a partition spike ID, edit snapshot, edit data files count, etc. This kind of data information. And then in the middle, here is a manifest. It is also stored in an Avro format, but we convert it into JSON format to make it more human readable. It has like status, snapshot ID, and then data file. Remember that for each manifest, it can point to 1 or more data files. So here it points to 1 data file, which is the parquet file, especially used to store the data of the region table. And then on the right, here is the table metadata. It is stored in a JSON file. It records the metadata information of this table, like the location, like the schema. You see here, it has 3 fields: a region key, name, and comment. And also there's a whether this is required or not, what is the type of this field, etc. And also, you'll see that here are some relationships among these 3 files. For example, for the manifest here, as what I have mentioned, it has like a data file, it has a file path and a file format, which is a parquet file. And then, for example, here you see there's a partition spike ID shown in the manifest list. Also, this is reflected in the table metadata here. So because when we create the aspect table, we didn't especially assign the partition mechanism. So the fields here is just an empty list. Also, you see here on the manifest list, there is added snapshot ID, and then the ID is of a long type. In the manifest, you see here, there's also a corresponding information about, related to that. The status is 1. 1 means this is added. And then there's also the same snapshot ID, exactly the same, and recorded in this field. So here is some structures related to these files, and I'll put them all together to construct an aspect table. So how we achieve the mechanism to load the data and to write the data and to read the data. So there are two paths. One is a write path and the other is a read path. So here, what I want to do is to introduce more about these two paths in the Presto Aspect connector. First, let's go to the write path. Suppose that the customer found a CTAS request, a create table as select request to the Presto server. And then the Presto server will first load data from the data source. And then for the next step, it will need to write metadata to the metastore because we need to construct the metadata related to the Iceberg table first about some like manifest this kind of information. And then we'll need to write data files. For example, take the previous TPCH dataset as an example. It will be like a Parquet file which store the region information. So we'll write this Parquet file into a data sink. It can be, for example, HDFS or GCS bucket. At the same time, we'll have a read path. In a read path, the customer will send a SQL query to a Presto server. And then it's quite straightforward compared with the write path. The Presto server will load metadata information from the metastore, for example, from manifest files from the Iceberg table to get information about the data files. And then it will load data from the HDFS or GCS buckets. For example, load the TPCH Parquet file and get information about it and then return the results to the customer. So that's the read path of this information. And here we also deployed the whole thing in a Devil Presto server. And at Twitter, we are using like Zeppelin notebooks, which is a web-based analytical tool to help us to run some queries against the Presto servers to get some results. So here is an example notebook that we have created to query the data through Presto Iceberg connector. So here in a Zeppelin notebook, here's a prefix. You see here, this is a JDBC Presto-Iceberg. This is called the prefix in Zeppelin. It means that it usually gives us, it is called the interpreter that can have access to a specific Presto cluster. So here, this is actually points to a Devil Presto server, which we have enabled Presto Iceberg connector. And then we use aspect.tpch, and then we ran two CTAS statements, create table if not exist from the nation and customer. So these are two new tables in Apache Iceberg format. And then we ran a SQL statement with a join command. Like to join the customer, the newly created customer and the newly created nation table together and get some information about customer's name and their nations. So here you see that this is the table underneath shows the query results from the Presto site, which has enabled the Presto Iceberg connector. So you'll see this is a general idea of the whole thing, that how we use the query, the Presto Iceberg connector to query data or some write data to the Iceberg table. And also we are having some future work to do to improve the current work. For now, we have sent a PR to the Presto repository, which has a basic support like the read path, the read path for the Presto Iceberg connector. We are planning some future work that to help us to improve the current work. For example, for now, we only support Parquet files. We also want to add ORC support into the file format. For now, we also would like to add a snapshot support to help us to add like snapshots So in that case, when the user ran the query, the user can select with the specific snapshot to run the query. And also we want to support like schema evolution, like adding new columns, dropping columns, renaming columns, etc. Also, we also would like to add like time travel and also the version rollback features in the Presto Iceberg connector. Yeah. So that's mostly what I want to talk about today. I'm always ready to help. So if you have any questions related to like Presto at Twitter or the Presto Iceberg connector, feel free to reach out to me in the Slack channel. And that's all I want to talk about today. And thank you. Have a nice day.